Hello everybody and welcome to the NPTEL online certification course on microelectronics devices to circuit. Today's lecture will be primarily concerned with common gate and common drain amplifier configuration. In our previous schedule we had looked into common source amplifier with source degeneration resistance as well as without source degeneration resistance. We also saw the advantage of having an source degeneration resistance. And the advantage primarily was to do with enhanced bandwidth, but a reduced gain and more stability. What we will do today is have a look at common gate configuration and common drain, but please take into consideration that most of the time common source configuration is used as an amplifier because of its relatively high gain, which depends upon the value of transconductance of the MOS device under study. So, higher the transconductance, we remember yesterday in our previous discussion, if you look very carefully what we did, what we saw was that the gain in general is considered to be equals to GM times RD, right. This we have already learned. Well, GM is the transconductance of the device and RD is the drain resistance. Now, this GM we have already discussed this point that is relatively insensitive to VI, right, which means that to input voltage, which means that GM should not be a function of VI. In reality it is not true, and therefore GM happens to be a function of input voltage, but if your VM or VI is relatively a small signal, then my GM is considered to be constant, right, and that is under that condition we say that my linearity is sustained and I am in the saturation region. We have also seen in the previous interactions and discussions that the input impedance of a MOS device is always infinity. So, R in is typically infinitely large because you are actually feeding your signal to the gate side, and since the gate side has got oxide layer inbuilt into it, you will not have any current, and therefore your resistance, which is voltage by current, since your current is approximately equals to 0, you get R equals to infinity, and that is what typical input resistance of an amplifier is all about. Output impedance will depend upon many factors, but typically it is RO parallel to RL, right, where RO is the resistance offered by the device itself. RO should be small, parallel to RL or RD, where RO is basically the resistance offered by the device itself and RL is the resistance offered by the external source. So, with this basic logic or with this basic understanding, let us now undergo what is known as a common gate amplifier. In the common gate amplifier, you need to therefore ground your gate. So, if you look at this diagram here, this is your NPN transistor which you see, or NPN sorry, it is a N channel MOSFET which you see, and its gate is basically grounded here, which means that this is also referred to as gate grounded configuration, right. So, this is gate grounded configuration, and this is also referred to as gate grounded configuration, and the gate is grounded. Please understand, therefore, you are inserting the signal to the source end of my gate, right, and you are extracting the signal from the drain side. So, this is your V sig is my input signal and R sig is my resistance offered by this voltage source, resistance in the series to it, typically relatively very small, and Rin is basically the resistance offered by the device looking from the source side. So, understand, looking from the gate side it was infinitely large because there was an oxide layer, but looking from the source side it is not infinitely large, but the typical value is 1 by GM, right. So, I will not derive it here, but a source from the source side, if you want to look in a MOS device, the resistance offered by it is 1 by GM, right. So, higher the transconductance of the device, lower will be your Rin, and intuitively you can understand why is it like that. If you remember, GM was equals to del ID del VGS, right. So, if you take 1 by GM, it is just the reciprocal of this one and you get del VGS del ID, right, which means that for how much change in ID I should get for a typical change in VGS, and if you look at the dimensions, it is basically in ohms. So, this is the resistance offered by the device when you are looking from the source end of its operation. On the right hand side which you see here, which is this one, if you look at this one, we are assuming that the diagram is exactly the same which you see on left and right, but here I am assuming that my impedance looking from the drain side is actually equals to RO. With this knowledge, let me just do a small derivation, brief interaction of CG amplifier. So, this is basically your common gate amplifier, right, amplifier, and if you solve it, I get Rn equals to 1 by Gm. This we have already seen just now. I can say Vi equals to V sig into R in upon R in plus R sig, right. R in is the input voltage, input resistance which you see, and V sig is the voltage of the signal which you see. Therefore, I can write down Vi equals to V sig signal divided by, right, divided by 1 upon 1 plus Gm times R sig. How do I get it? So, how do I get it? If you divide numerator and denominator here by Rn. So, if you divide this whole by Rn, numerator and denominator, I get 1 in the numerator, I get 1 in the denominator plus R sig by Rn, but 1 by Rn is nothing but Gm, and therefore, I get Gm times R sig. Therefore, I get input current II is equals to Gm times Vi. Please understand here, why are you getting an input current? Because you are feeding the voltage through the source terminal of the MOS device, right, and that is the reason you are having an input current, right. This would not have been there provided you were actually doing on the gate side, right, and that is the reason it is Gm times Vi. So, therefore, the drain current which you get is also therefore equals to Gm times Vi, but it will be with a negative sign. So, this will be minus Gm times Vi, negative Why? Because there is a phase shift between there, because the current direction will be just reversed as that of the source side. Therefore, I get Vo, which is output voltage, also referred to as Vd, equals to minus Id times Rd parallel to RL. If you solve it, I get Gm times Rd parallel to RL multiplied by Vi. So, Vo by Vi is nothing but, therefore, Vo by Vi is nothing but Av, and that is equals to Gm times Rd parallel RL, right, and that therefore, I can safely write down this to be equals to Gm times Rd, as RL is much larger as compared to Rd, and therefore, I get Av to be equals to Gm times Rd, you see here, right. So, your common gate amplifier is basically Gm times Rd here, Av gain, right, is Gm times Rd. So, what I get from here is that that it can act as a unity gain device, provided R sig is approximately equals to 1 by Gm. So, if it is 1 by Gm, the cancels out, I get 1. So, 1 by 2 half. So, when I get half here, I can have Vi to be equals to half V sig by half, right. So, half the V sig is available to you in the input side of your device, and therefore, your gain will also reduce in that sense. One thing is there, and the second part of it is that it is one characteristics is that it is non-inverting in nature. So, it is non-inverting, which means that the phase, there is no phase change between input and output, right, because you are feeding from the source side, taking from the drain side. There would have been a phase change provided you had taken it from gate side and taken from the drain side, output would have been from the drain side, but in this case you are feeding from the source side and you are taking from the drain side, and therefore, it is also referred to as non-inverting design with no phase shift between input and no phase shift between which point, between input and output, right. First thing. The second thing is, if you look very carefully, impedance of this device is approximately equals to 1 by Gm, which we have already understood. Now, this is relatively very low, because Gm is relatively very high, right, and therefore, Z is typically low. So, the input impedance of the device in a common gate amplifier is relatively low, right. So, but we have understood that it should be low, and output impedance can be found out as Rd parallel to RL, and if RL is typically large, it is approximately equals to Rd, which you get ZO, output impedance, right, for a common gate amplifier. One small thing which I just wanted to point out to you here is that if you look for example, if you look from this side, this diagram here and just concentrate at this particular point, then let us see what is the problem, one small problem area of common gate. So, please understand, you are feeding the signal from this R sig, right, V sig, right, and this is R sig, and you are feeding it onto the source terminal of the battery, source terminal, and gate is grounded, right. If you look very carefully, when this so for the device to be on, gate to source voltage should be larger than the threshold voltage of the device. That is the basic concept we have been learning for we know very well. Now, if gate is 0 volt and let us suppose my source voltage is positive and say it is 1 volt, then 0 minus 1 will be equals to 1 minus 1 volt, and therefore my device will be in cutoff, right. And that is the problem area, that whenever my device goes to negative or the positive, or if let us suppose I have a positive and negative cycle, then for the positive cycle you will automatically have this problem. In the negative cycle, let us suppose this is minus 1, then what I get 0 minus of minus 1, which is equals to plus 1, and then let us suppose threshold voltage is 0.2, then obviously my device is in the on state, right. So, in the negative half cycle it works fine, but the positive half cycle you do have a problem that your device might be even in the cutoff state, right, and that is the one of the problem areas of common gate as such, but we will discuss no further than this in this case. Secondly, why there is no phase difference between drain and source, because you will, if you look very carefully, whatever potential you are giving here, the same potential will appear at this edge, right, because the same current has to flow between these 2 points, and therefore it is not out of phase, it is perfectly in phase, and therefore basically it is a non-inverting, common gate is basically non-inverting amplifier, and the second thing is its Z in is very low and Z out is relatively high. Okay. With this okay, one more thing which maybe I can discuss with you is one more problem area is that now you see very effectively your source voltage is changing, right, source voltage, right, is always changing, right. Why it is changing? Because you have applied a V sig here. Now, the signal voltage will change and therefore, this voltage will go on changing, right. Once this change, obviously VSB, let us suppose my base is grounded, right, base is grounded, then VSB will also change, source to bulk, and therefore my threshold voltage, which you remember will be a function of VSB, which was, so in the previous all my examples since my source was grounded, and even if it is not grounded, provided in an NMOS device, I am able to plug my bulk to the most negative part of the potential, then my VSB will be approximately equals to 0, and therefore I will get automatically no body effect. So, under the condition that your VSB is equals to 0, you will never have a so there will be no body effect, and your VT will be effectively constant, right. But in this case specifically, when you are doing a common gate structure, you end up having a variation in the voltage on the source side, and therefore source to bulk voltage goes on varying, and therefore the threshold voltage becomes a strong function of the source to bulk voltage, right, and therefore threshold voltage will vary, and therefore we are not sure whether the device will be on or off at particular point of time. So, this is one of the problem areas which people face when you are doing a common gate translation. We come to the next part, and that is basically your, so just a minute. So, common gate we have finished. We see that AV0 is GM times RD, and your output impedance is approximately equals to RD, and input impedance is 1 by GM, right. So, it is just common gate configuration which you see. Let me come to common drain architecture. Common drain, as I told to you, therefore, when it is common drain, your drain will be grounded, and therefore it is also referred to as drain grounded architecture. It is referred to as a drain grounded architecture. This drain grounded architecture which you see is primarily means that the drain has been grounded to obviously to the 0 potential here, and applying a signal again back to the gate side, right. So, only in one condition, which is CG, which is common gate, is the point where you apply the signal to the source side. For all other conditions, you have, for all other amplifier configurations, you apply the signal voltage onto the gate side. So, I am applying a V sig here through an R sig here, and applying to this. Vi is the available input voltage and Rn is the input impedance. So, Vi is the available input voltage out of, so V sig was your total voltage given to the device, out of which Vi appears as the input voltage to the gate side of this device, and you get something like this, and then you have RL here, which is the load impedance, and there will be a voltage, output voltage will be seen from this side. So, if you do a short channel, sorry, a small signal analysis and maybe replace it by a T model, then let us see how it works out. So, if you see very carefully, let us, this blue box is my equivalent circuit model, and I will explain to you how we got it. First of all, see, so this RO is between this point and this point, and this primarily comes out because of CLM. So, channel length modulation, remember, I am assuming that my output impedance will be infinitely large, not true, there will be a finite impedance available between the drain. So, this is your drain end, this is your source end, and this is your gate end. So, you will automatically have a impedance or a resistance between drain and source, which you see in front of you, this one, and therefore, this is your source actually, and therefore, you get this thing. What is 1 by GM? 1 by GM is nothing but this device itself, because remember this is basically a VCCS, a voltage controlled current source. So, I can safely write down the resistance offered by the device is 1 by GM looking from the source end. We discussed this point earlier also, right, this is the point, and this RL is basically a resistance offered by external load. So, RL is external load which you see in front of you, and this is the MOSFET current source. So, I am assuming this to be an ideal current source, right. So, its output impedance is infinitely large, and then what I am trying to do is its corresponding resistance looking from the source side is given by this. Now, why I am adding this here? The reason is very simple, that since no current is flowing through this point, because it is a gate terminal, no current, I can safely join the gate terminal to this particular point without violating any Kirchhoff's law, because there is no current flowing through these two arms. So, what is the net equivalent circuit? I have R0 here, 1 by GM, RL, and a current here which is basically an ideal current source, and I get V sig at this particular point, right. Now, let me explain to you the CD, common drain amplifier. What you get is Rn equals to Rg, the gate voltage of course, and Vi therefore will be approximately equals to V sig. And the reason is that, if you remember, the concept was that if you remember previous turn or previous discussion, we saw that V sig was actually getting divided by Rin and Rin plus Rg, right, Rg. Now, if Rin is relatively very large, this cancels off, and therefore, I get Vi equals to V sig. So, under the condition that your input impedance is relatively very high, I automatically get my V in equals to V. So, whatever V sig you are giving, say you are giving a 2 volt supply, 2 volt will appear across the gate of the MOS device. With this knowledge, I can write down Vi equals to V sig, right, Rg upon Rg plus R sig, right. So, if you solve it, I get AV0 to be equals to R0 divided by R0 plus 1 by GM, and therefore, 1 by, if you see, is very large as compared to 1 by GM, right. Your this R0, which is primarily because of the CLM phenomena, is very large compared to 1 by GM. So, I can safely write down that AV0, right, will be approximately equals to R0 by R0, because this will be very small as compared to R0, and therefore, I can safely write down this to be equals to 1. Therefore, I can safely say that a CD amplifier, a common drain amplifier, is having a gain of unity, which is basically meaning unity gain amplifier. This is basically a unity gain amplifier, right. This is a unity gain amplifier which you see. So, it is basically used as a buffer, right. Now, if you come here, therefore, so you see AV0 is 1, Rin is infinity for reasons which you have already understood by now, because Rin is infinity. Why? Because you are actually seeing from the gate side. So, as I discussed with you, infinity. Ro is basically the impedance looking from the drain side onto the device, right. So, if you come back here, you are looking from the drain side onto the device, means you are looking from this side onto this side, which is nothing but 1 by GM as we discussed earlier. So, if you are looking at output here, the equivalent circuit model, if you are looking from this is my output and you are looking into this region, right, from the gate, sorry, not from the drain side, sorry, I will just explain to you. This is my output, right. So, you are looking from this side. Looking from this side is basically looking at the source end of the device, right. Source of the device means 1 by GM. So, I get R0 equals to 1 by GM, right. So, if you want to use it as a impedance matching purposes, you can do that, provided so this will be somewhere sitting in the buffer of IO design, right. It can be used as a buffer. Why? Because since its AV is approximately equals to 1, it does not give you any gain, but what it does is that its input impedance is relatively very high, Ri is relatively very high. So, if I have one block here, another block, this is my, and I have another block here. So, this is my CD, right. Since its input impedance is infinite, if the output impedance of the previous stage, say this is stage number 1 and this is stage number 2, and you want to have the maximum signal to be transferred from stage 1 to stage 2, then if the output impedance of stage 1, Z out of stage 1 is infinitely large, then you connect this to this very easily, because input impedance of CD is infinitely large. And if I can connect to the like this, then CD drives stage 2 whose input impedance is 0, right. And therefore, I can have a maximum power being transferred from 1 to 2, and therefore, reliability is not a major question, provided you have a CD gap in between them, right. With this knowledge, we have almost done the most part of the design functionality of a common gate, common drain. Let me just recapitulate therefore all the 3 configuration to you. The first is common source, as I discussed with you, obviously is AV is much larger than 1, right. Input impedance is the Thevenin equivalent or the total resistance offered by the device. Output resistance is moderate to high. We just now saw source, so this is the common gate, AV is greater than 1, current gain is approximately 1, input resistance is low and moderate to high. Okay, common drain, this is also referred to as CD, a common drain. Common drain is basically source follower. I will explain to you why is it source follower. So, why is it is also known as source follower. The source follower primarily means that whatever voltage you give on the source side, right, exactly same appears across the output. So, source follower means whatever input you are giving in the source side, right, exactly same thing appears in the output side without any gain or loss, because your AV equals to 1, and therefore, this is also referred to as a source follower. So, how do you define a source follower? Source follower is that the signal on the source side of a device will be exactly equal to the input signal, and therefore, it is also referred to as source follower with AV is approximately equals to 1, right, gain is approximately equals. So, common source, common gate both have very high gain, out of which common source has got a much higher gain. Output impedance is relatively high for both of them, but for source follower the output impedance is low because it is 1 by GM, and the input impedance is also relatively small, which you see in front of you. So, what we have done till now therefore is that we have finished with configurations of common gate, common source, and we have also seen into the fact of Z in and Z out. Therefore, we are now in a position to use these MOS devices under various configurations. So, if I want a high gain, fix it to common source. I do not want a high gain, I want just impedance matching, do common drain or source follower. If I want to go for moderate low input impedance, go for common gate structure, right, and therefore, you will be able to handle all of them independently in order to design it, right. With these words, I thank you for your patient hearing. Thank you.